Hi there. So we continue our journey on 6502 assembly by learning how to add and subtract numbers. So let's dive into it. We're going to learn a new operation called ADC that we use to add numbers to the accumulator. And AD is add, and the C, we're going to talk about what the C stands for in a minute. But what we're doing here is we start just with ensuring that the accumulator contains 0, and then we are adding a number, in this case just the number 1, to the accumulator. In this case, it's kind of like what an increment of the accumulator will do, but of course, I'm just using one as a first example. We can add arbitrary numbers here. So we put the result in some memory address. It's just a memory in the 0 page. And then we have a routine to print so we can see the output of our sum. So we load the result into the accumulator again, we print byte, and we just print carriage return, a new line. So let's see this program in action. Okay, as expected, 0 plus 1 is equals 1. So now let me add, I don't know, 5. Okay, now 0 plus 5 is 5. That makes sense. But now let me show you something different here. So what do you expect here? We have FF, which is basically 255, and we add 0. So let's see what we get. We get FF, right? FF plus 0 is FF. And what if we add 1 to FF? So we would like to have 256, right? But we get 0. So you see what's going on here. The maximum we can represent, the maximum value we can represent with a byte, with a single byte, it's 255, right? It goes from 0 to 255. And if we add 1, 256, we basically run out of precision. But still, I mean, of course, we may want to add 2 bytes and then use, instead of 1 byte to represent the answer, we may want to represent 2 bytes to represent the answer, right? So we extend the precision by just increasing the amount of memory that we are using to store the numbers. However, there must be a way that we know that we have basically gone, I mean, we have this 0 here, it means something different than just plain 0, right? 0, 0 would really means 0, but this one means FF plus 1. So how do we know that it has returned to the 0 value because it has gone over the maximum possible value, or in other words, it has overflown its precision? So this is accomplished using a flag that's part of the 6502 registers called the carry flag. So the carry flag starts clear, so it's basically its value, it's 0, it's false. But if you do an addition that overflows, then the carry flag is set to 1. So let us go to the assembly lines book and understand a little better what that means. So what you see here is we have a byte, 8 bits, to represent arbitrary numbers between 0 and 255. So if all the bits are 0, then we have 0, of course. And then we have certain values that these positions represent. So this position means 1. So if it's the bit is 1, then it means that we have the value 1 here, right? All the others are 0 and this is 1. This position represents 2. So if we just turn on this bit, that means 2. But if we turn on this bit, the bit that means 2 plus the bit that means 1, we have 2 plus 1, we have 3. And then this bit here represents 4. This bit here represents 8, and so on. And you can imagine that as we increase the values, eventually we get to a point where every bit is filled with the value 1. So that's our maximum possible value that we represent with a single byte. That's 255. And then when we add plus 1 to this number, it goes back to 0, but then it sets the carry flag to 1, meaning that it has overflown. So this value on the carry flag means that we should add 255 to the value that we have here. So for instance, so it's the value 255 plus the 1, right, that we have from the carry. And we can also show that when we set when we set the carry flag, this will impact the additions that happen after that. So let me show you what I mean. So we say, okay, we have loaded here. Let's just load the accumulator with 0. And then let's add 1 to the accumulator. So we load the accumulator with FF, and then we add 1. And then this is going to cause an overflow and set the carry flag. And now basically overwriting the contents of the accumulator with 0 again and adding 1. So what we would expect here is to see the value 1 as the result, right? Because we basically ignore this. I have overwritten the accumulator with 0 and started the sum again. So this should have no effect. But this is going to set the carry flag. So let's see what happens when we set the carry flag. So you see, instead of 1, we get 2 here. And what if we add 0 to start with 0 and then add 0? It should be 0, right? That's what we want. But it's 1 because this 1 actually is coming from the carry flag that got overflown here. And this is handy. We can use this in a certain situation that I'm going to explain soon. But right now we just don't want it, right? It's like these two things are completely separate additions. But something that happened here, which is the setting of the carry flag, is leaking in this part here. And we don't want that. So what we have to do is we have to add a new instruction here that's CLC. And that means clear carry flag. Oops. Yes, clear carry flag. So here basically we are setting the carry flag to 0. So this now should be completely independent of what happened here, right? Because this is going to set the carry flag, but then we clear it, and we're basically saying we want to start a new arithmetic operation here completely from 0. And then we do this. So I'm gonna revert back to add 1. So let's see what we have now. So now we get the result that we expected, right? So now we have, we are adding 0 to 1, and that's resulting in 1. And just to show you that this is what's going on, if I comment out, I have again, I have 0 plus 1 equals 2, because we have that carry flag from the previous operation. And now we don't. We have what we actually want. And I promised to explain what this C means, and you guess, now it means we add with carry flag. It's basically we say, okay, we want to add whatever value we inform here. We want to add that to the accumulator, and we want to set the carry flag. So I mentioned that the carry flag actually has a point, and there is a situation where we might want it. So let me explain it. Let's say we want to make this, let me just remove these lines. So we want to make this, right? We want to get the number 256. We want to sum FF and 0, 1, and that of course is going to result in 256. But we cannot represent this with a single byte. We need 2 bytes to do that. So let's get that second byte then that we need. So I will just start by loading the accumulator with 0. And now I am going to add 0 to this new byte, right? Because we already have made the addition that we wanted here. This we are just setting the other byte, but because we have the carry flag, this is actually going to set it to what should be the most significant byte value. And I'm gonna show you what I mean by that. And now we store this second byte just after the byte next to result. So we will have now 2 bytes instead of 1. The first one contains the first part of the sum, and the second contains the second part of the sum. And you agree that if we sum all these terms, we are adding FF and 0, 1. That's what we want. I will also change a little bit our print routine. So now we print not only the byte on result, but we also print the byte on result plus 1. And we put a space between the two. So let's run this. Okay, so that's the outcome, 0, 0 and 0, 1. Now let's try to convert this to a decimal value. So remember, 6502 is big endian. So it means that this byte here contains the most significant bit. So when we type this for conversion, we actually have to put 0100 just for the regular order. 0100, and that's 256. So here you see that we can use the carry flag as a means to make an addition using 2 bytes and make sure that the second byte that contains the most significant bits, they are going to be added 1, which means increasing it by 255. So we end up with 0 here, but that 0 is carried over, I'm sorry, we have 0 here in the least significant byte, but the 1 from the carry flag gets carried over to the most significant byte, and that one here in this position means 256. So yeah, this is how we can do addition using ADC, and we can make either, if we know that the result will fit into a single byte, we can just use a normal ADC. And if we know that this might require larger precision, we can use 2 bytes, and then we can use the carry flag as a means to be able to populate the 2 bytes. Okay, so let's think about this for a moment. So we have, if we want to have 2 bytes to represent a number, we're going to need a low byte, and this one is representing the least significant bits. So for instance, this one would mean 1, right? Because a bit on here means 1. If we put this bit on, it means 2, and 2 plus 1, that this would be decimal 3, right? But if we were to, the high and the low byte, they are in reverse order, because this is the order that 6502 uses. It's the big endian processor, so the most significant byte comes at the end. So when we think about adding numbers, so let's say we have number, this is decimal 1, right? And let's say we have this number, that's decimal 2. So if we add them, so we get, so we add this number to this number, and then what we get is this. Now, if we were to, let's say we have here in the low byte, we have 255. So what we have here is 255, and we add 1. What happens here is the low byte gets all zeros, but then the high byte gets this 1. So this is the carry, right? So the idea is when this overflows, we make it 0, but then we carry the 1 to the next byte, to the most significant byte, and that means 256. We start with 256, and if we were to add 1 again, so this is 256, and if we were to add 1 to this 256, then we would land with this, and that's 257. So this is the point of the carry flag, is to indicate that we have to carry 1 to the next operation, because it's always assumed that we will first operate adding the low byte to the low byte, and then adding the high byte to the high byte. And that's why having the carry flag on, having the carry flag set, will change the behavior of ADC, and it's actually make it add 1 more. So you might imagine that subtraction is the opposite, and that would be correct. So for subtracting instead of carrying, we need to borrow, which means that in some cases we if we want to, if we have an overflow while subtracting, we actually want to subtract one from the high byte. We want to subtract the first position of the high byte. So in order to save flags in the register, so what 6502 does is it uses the same carry flag. Also, I mean, if we are subtracting, the carry flag now is going to indicate that we are doing a borrow. But now the reasoning is the opposite. So if the carry flag is on, that means that there is no borrow. So the standard behavior, let's say, is the standard behavior that we want to have a no borrow, we need actually to set the carry flag. And if the carry flag is off, and this is going to be caused by an underflow when subtracting, then there will be a borrow. So what we want, by the way, the 6502 instruction for subtracting using the carry flag, but yeah, in this case it's not really carry flag, it's a borrow flag. It's SBC, as in, yeah, you guessed it, subtract with carry. And because the standard behavior that we want is to have no borrow, we actually have to set the carry flag before we do a subtraction. And we do that with the instructions SEC, which stands, of course, for set carry. So let's see this in practice. Okay, so here we can see an example of subtraction. So what we are doing here is start with 255 and subtract 0. And this is not what we wanted, right? Because if we are subtracting 0, we should still get FF and not FE. Actually, we subtracted 1. And the reason is the carry flag is clear right now, which means that there should be a borrow. So what we have to do here is to set the carry flag. And then it should do what we expect. Yep. So now let's subtract 1. Subtract 2. So now it's working. And you can easily imagine how we can create the opposite operation of the sum that has a 2-byte result. We could here do a subtraction to a 2-byte result, taking advantage of the carry or borrow flag behavior. But I will not demonstrate this because I believe this is now trivial. And anyway, you can check the book Assembly Lines for an example. Okay, that takes care of our episode on adding and subtracting using 6502 assembly. And I'll see you next episode where we discuss disk operations, disk I/O. See you there.